right, gang, part 3, work, power, and energy. Okay. We're going to talk about conservative and non-conservative forces. And the work done by a conservative force depends only on the initial and final position of an object acted upon. So an example of a conservative force is gravity. The work done equals the change in the potential energy and depends only on the initial and final positions above the ground and not on the path taken. So if we talk about the initial total mechanical energy as being the kinetic plus the potential, that equals work. And the work equals the final plus the kinetic energy as well. So the original energy has to equal the final energy. Now that's a conservative system. Now when we have something called a non-conservative system, we will have the kinetic and potential energy at the beginning. We'll have work done, but some of that work will be lost in mechanical energy. So things like friction causes lost mechanical energy in heat and sound. And so the final kinetic and potential energy do not equal the original. They are actually less than. But what ends up happening is it's less than the energy itself, but you have to add this, you either have to add energy on the product side or on the reactant side, depending on where the energy of whether it's lost in the beginning or it's lost to the environment. So we'll talk a little bit about this. Let's look at some more slides. So friction's a non-conservative force, and the work done is moving an object against a non-conservative force depends on the path. So for example, the work done on sliding a box of books against friction from one end of the room to the other does depend on the path taken, because if we go from path 1 to path 2 in a straight line, that is different than if we go from point 1 to point 2 in curve. So that energy will be different as well. So we've kind of touched on the work energy principle already in class, but on your formula chart, it says that delta E equals work. So really what that means is the work of a resultant external force on a body is equal to the change in the kinetic energy. So it could be the change in kinetic energy, or it can be the change in the potential energy. But really, when we look at it, it's that delta K is really that delta E on your formula chart. And we can expand that out to be the kinetic energy at the end minus the kinetic energy at the beginning is equal to work. And we can expand it out even further to look at it as kinetic energy as 1/2 mv squared minus 1/2 mv squared. And those v values would be the change in the velocity that you have. Because if you have a force, then you have an acceleration. So from this first location to this second, there is going to be two different velocities because it's accelerating. So really, when we talk about this force, it's mass times acceleration, and then multiplied by distance. So that's the same as saying that the kinetic energy of here, this final position, minus the kinetic energy here, is going to give you that velocity, or excuse me, is going to give you that work also. So there's just a lot of different ways to look at it, but you can expand that formula out to equal that. The second one would be that the work is equal to the change in the potential energy. So if we say that it's the W is equal to the change in our U, then we could expand that out and say it's the mg change in final height minus initial height. So something to realize on these things is that when we look at it like this, lots of times we're going to be able to say, oh, hold on a second. And so we're going to end up being able to say that force times distance equals mg change in h. Well, we can also look at it as mass times gravity times distance equals mg and delta h. So something to realize is that these masses cancel out, and they really ultimately are the same thing. And that's why those formulas work that way. So just a way to think about it. Okay, so for mechanical systems involving non-conservative forces, the total mechanical energy equals the sum of the kinetic and potential energies minus the work done against friction of the object. Because friction, remember, is a negative work. It's going to cause a negative work value. So you're really looking at the total work minus the negative work, and then that'll equal your final work. So when you look at it that way, you can see over here, let me get my screen animating again. So as that height changes, the kinetic energy increases, then the potential energy goes down. But then when we get down here, notice that we get into negative work, and that takes away from my overall energy because we're in a frictional surface now. So that'll take away from that energy, slow me down eventually because it is negative work, so it's taking away from the kinetic energy. So some more non-conservative situations would be when we have potential energy and it's going to push this down and it's going to cause those molecules to heat. So the kinetic energy of the weight, and then we'd end up with more heat. So still more heat. So the heat is actually a non-conservative force. So the kinetic energy will decrease as the heat goes up. So that's kind of one of those thought processes as well. And then chemical energy to kinetic energy plus potential to less kinetic and more potential to heat energy, which is just the kinetic energy of the molecules when it actually explodes. So those are things where we're changing it from one type of energy to another, and then it's changing to a different one, but it's considered non-conservative because it doesn't stay within the system itself. It's not just kinetic and potential energy anymore. All right, so summary about what we've talked about so far. We've talked about the energy gains or losses, and we have energy, we have gravitational potential energy, which is on your formula chart as U equals mg change in y. We have our spring potential energy formula, which is our U equals 1/2 kx squared, where k is our spring constant, and x is our displacement of our spring, so either the compression or the stretch. And then kinetic energy is our 1/2 mv squared on the formula chart. And then remember, work against friction would be work times our friction would be equal, that work is equal to our frictional force multiplied by our displacement. So normally that, since it's against friction, it's a negative value, so because of that frictional force. So conservation of energy, basic rules are is that your mass times your gravity times your height originally, plus your kinetic energy, plus your spring potential. All of those could be equal to, or all of those added together would equal all of your final ones, plus if it's non-conservative, or work against friction. Remember, you could move that to the other side and say minus the work against friction, for your originals would equal your finals. So it's just different ways of looking at all of those, but it's everything that's in the box added together. So the summation of this first box equals the summation of the second box plus the third box. So remember to use absolute value signs for the work of friction because it's a loss of energy if you're using it on this side, on the product side. If you use it on the reactant side, then, or your original side, then you'll use a minus. Alright, so general case to kind of think about. In real life applications, some of the mechanical energy is quote unquote lost due to friction, and the work due to a non-conservative force is given by our work equals our change in kinetic energy plus our change in potential energy. So we can do some different values here with a roller coaster, and that's why, could we really go from point A to point B to point C? Is that possible to do just as we're going from left to right? The grand scheme of things, no, because you're not ever going to have more energy to get up the hill to go that 8 meters. So there's some nice things about that. And then I have funny little here that since it's starting to get snowy out, or it's not snowy here, but it's starting to get cold. But it's just a fun little one about the fact that, you know, we think too much, but it's lots of fun to look at. You guys have a great evening.